I'm going to break this problem up into three parts. There's the charging process. That's when both capacitor C1 and C2 is hooked up to a 24-volt battery in parallel. So that means both capacitor C1 and capacitor C2 are going to be charged up to 24 volts. There is a reconfiguring part, which means that one of the capacitors, that's C2, is flipped around. So they're both unhooked from the 24-volt battery, and one of the capacitors is flipped around and connected to capacitor 1. And this no time has passed. You just reconfigure and stop the clock right when you make the connection so that no charges are able to redistribute. And then the final condition, where after a long period of time, or I guess a certain amount of time goes by to where charges redistribute and reach a temporary equilibrium. That's going to be called the final condition. Okay. So first of all, for the charging, we know two things: the voltage across C1 and the voltage across C2 is the same as the voltage across the battery, and that's 24 volts. We can go ahead and say that C1 and C2 are just properties of the capacitor, so that will never change. And you can get the charge that comes about from both capacitor 1 and capacitor 2. So I call that Q1 initial, Q2 initial. That's just going to be C1 times V. This is going to be C2 times V. And if you do the calculation, this times that, or this times that, comes out to be 5.28 times 10 to the negative fifth power coulombs. This is going to be 2.88 times 10 to the negative fifth power coulombs. Okay, so that's the charging part. When you reconfigure, some things you know. The first thing is that all of the conditions will remain the same. The charge on both capacitors will remain the same, and the voltage will remain the same as well. But what we do need to realize is that during the reconfiguration process and even afterwards, the charge cannot remain in equilibrium. For example, you see, when I say equilibrium, I mean the same for both capacitors. That's what I meant to say. So that means, for capacitor 1 and capacitor 2, the charge here is not going to be the same as the charge there. Because of the difference in capacitance, the charge here might be bigger than the charge here, or vice versa. So one thing we do know for certain, though, is that the voltage across them, especially in the initial process and actually even afterwards, will remain at 24 volts. Or will actually not for any time afterwards, but right when we hook them up, will remain at 24 volts. And then from there on, it's an equilibrium, for temporary equilibrium. From there on, it's going to redistribute the charge, and then the voltage will drop because of that redistribution of charge. First thing you want to do is you want to get a universal voltage across these two capacitors, because like I said before, the charges will distribute, they'll be different. So there's no universal except the voltage across them after the initial redistribution happens. So we can get that by looking now into the final condition. So first of all, the equilibrium capacitance for two capacitors in parallel is going to be this capacitance plus this capacitance. So remember, in capacitor terms, parallel means you add the capacitances. That ends up being 3.4 times 10 to the negative 6 farad. You want to know the total Q on top and the total Q on the bottom. So after charge is redistributed, the sum of all charges on the top plate and the bottom plate can be thought of as now this new capacitor, okay, with a certain charge on the top plate, certain charge on the bottom plate. That's the same as this, certain charge on the top plate, certain charge on the bottom plate, when these two capacitors are now intertwined as into one universal capacitor. So in order to do that, you would say that the Q equivalent is going to be the sum of the two Qs on either the top of these two capacitors or the bottom of these two capacitors. Well, the good news is the same number. So we'll take the absolute value and say the initial Q on the top of the first capacitor minus, because this is flipped around, so it's now the negative is on top and the positive part's on the bottom. So we say minus the initial Q on the second capacitor. So this is going to equal to 2.4 times 10 to the negative fifth power coulombs. So you have the equivalent capacitance and the equivalent charge on the capacitance once the equilibrium comes about. Well, that's too bad. We want to find the individual charge on the capacitors. So in order to do that, we need to find out the voltage between the capacitor plates for each of these two. And in order to do that, we basically take the equivalent capacitance capacitor that we found here and find out what the voltage across these two plates is. That's the same as the voltage across these two branches. The voltage equivalent is going to equal to Q equivalent divided by C equivalent. And that ends up being this divided by that, which comes out to be 7.06 volts. And last but not least, since we have the voltage across both of these two capacitors in parallel, and we don't have to look at this anymore since we have all our data, we can now find the charge on each individual capacitor with their individual capacitance. So the charge on capacitor 1 after redistribution of charges is equal to capacitor 1 capacitance times the voltage across that capacitor after all said and done. And that's going to come out to be 1.55 times 10 to the negative 5 coulombs. For capacitor 2, the charge after all is said and done is the capacitance 2 times the voltage across capacitors 2's plates. And that's going to equal to 8.5 times 10 to the negative 6 coulombs. And there you have it. You have the charge after equilibrium is met of capacitor 1 and capacitor 2's plates and the equilibrium voltage.